Hello everyone. We are talking about Chapter 5, Lesson 2, which is talking about interpreting graphs. So the graph at the right shows the varying speeds at which Emma exercises her horse. So Emma's exercising her horse. The x-axis is referring to the time in minutes and 10, 20, 30, 40, 50 minutes. And the vertical axis or the y-axis is referring to how fast the horse is going, the speed in miles per hour. So here's 10 miles an hour, 20 miles an hour, and so. So let's just go. We have some different descriptions here, and we're going to see how these descriptions match up with the graph. So the first one it says is the horse walks at a constant speed for the first 10 minutes. So here, at 0, this is when time starts, and the horse is walking at a constant speed. So whatever this speed is, it's a walking speed. 10 miles an hour is up here, so they're not going too fast. It would probably be 10 divided. There's 1, 2, 3 sections, so each of these sections is close to 3, so that's, probably a little over 2 miles an hour. And it's walking for 10 minutes, and you see right there it's a constant speed, which means it's going the same speed this whole time. And it's going until 10 minutes. And then what happens is the speed increases over the next 7 minutes. So here, over the next 7 minutes, from 10 minutes, that's 5, and then right about there, 7, you can see that we were at about 2 miles per hour, but now our miles per hour is growing over these next 7 minutes, and now we're just under 10 miles an hour there. But if you see over the 7 minutes, the speed increased. Then the horse starts galloping at a constant rate for 20 minutes. That's a long time to gallop. And the galloping speed, so it just goes all the way up here. So it was increasing, and then it just jumps up to a full gallop, and the full gallop is consistent for 20 minutes. So each one of these is 5 minutes. So, from here to here would be 5, 10, 15, 20. So it's the same speed for 20 minutes, and it's going over, 20 miles an hour. That's about 3. So maybe, 23 and a half, 24 miles an hour, 24 miles an hour for 20 minutes. Then what it states is then the horse slows down over the next 3 minutes. So right here, over the next 3 minutes, it drastically slows down. And you can see the speed is dropping quite rapidly over the next 3 minutes. But it's kind of a consistent drop right down there. And then lastly, the horse walks at a constant speed for the next 10. So now we're back to the walking right here. From 40 to 15 minutes, we're back at our walking speed, which is, about 2 miles an hour or so, from 40 to 50, so that's 10 minutes. So this is just an example of a graph and of a horse, of Emma exercising her horse, and how someone may describe that, and how the description relates to an actual graph. All right, let's look at some examples. The first one is going to be example 1. So what we're going to do is we're going to relate graphs to situation. We have graph A, graph B, graph C. If you see here, the x-axis, time is represented by the x-axis, which is kind of a normal thing. For the most part, whenever you're dealing with time or seconds, it's usually going to be on the x-axis. And on the y-axis is height, okay? And for each of those, time, height, okay? So what we're going to do is we're going to choose the best graph which fits this particular situation. So let's go ahead and read it. It says the height of a tree increases over time. Okay, so that means that the height of the tree would be kind of small, and then over time it would get bigger, so the height would grow as time increases. But not at a constant rate, okay? So it doesn't increase at a constant rate. Going back here, all of these things, when it's a straight line like this, it's a slanted straight line, that is a constant rate. Right here, when it decreased in a straight line, that is a constant rate. This is just remaining constant, a horizontal line, remaining constant, remaining constant. Something that would not be constant would be something that wasn't a straight line. But when you have something that's a straight line, this is a consistent increase. This is a consistent decrease. This is just a constant rate there. But if it does not increase at a constant rate, if it increases but not at a constant rate, then that would be something that would be more of like a curved line somehow, or if it decreases but not at a constant rate. Decreasing would be, it would be going down, but it wouldn't be a straight line. It would be something of that type of thing. So this would be increasing, but not constant, but not at a constant rate. Whoops, that doesn't, let me rewrite that, but not at a constant rate. And this would be decreasing, but not at a constant rate. So whenever it says that, you know that what you're going to be dealing with is a curved line. But whenever it says constant rate, or constant rate, you're going to have some type of straight line. Like, like this particular graph right there. Those were all constant rates, okay? So we're going to go back here. So the height of a tree increases over time, but not at a constant rate. So it's increasing, but not at a constant rate, which means we're going to be dealing with some type of curved line. Which graph best shows this? So if we look at graph A, what we see is that the height of the tree is at a particular amount when time is 0. And the height of the tree remains the same as time increases. As time goes on, the height of the tree is the same. So we know that it is not going to be A, okay? I'm going to go to C. C, the height of the tree, this is kind of accurate, you know what I mean? It's going to start somewhere, and it increases. As time increases, the height of the tree increases. But what happens is that this is increasing, since it is a straight line here, it is increasing at a constant rate. And what our problem says, the height of the tree increases over time, but not at a constant rate. So it's not going to be a straight line. So we know it's not that one. Here, when we look at this one, B, we see that time is at 0, the height is at 0, the tree is growing pretty rapidly, but it's not at a constant rate. It's at a slower, it's fast here over time, you see, and then as time increases, the height of the tree doesn't grow as fast as it initially did here. So as time goes on, the height of the tree still gets bigger, but just not as bigger as it originally did when it first started. So this would be increasing, but not at a constant rate. So our answer, in fact, would be B. B would be the answer to that particular question. Okay? So now I want you to go ahead and try to check it out. Go ahead and look at example 1. Try that on your own, and then check back, and we'll see how you did. Oh, there's my pause dragon. Remember you to pause your device, press play when you're done, and we'll see how you did. Okay, we're back. It says the dimensions of the basketball court have changed over the years. However, the height of the basket has not changed. Which graph best shows this? So we are referring to the height of the basket, and the height has not changed. Okay? The height is not changed. So from the beginning of the game of basketball, the height has been 10 feet. Now when we play the game, even though time has went on, the height is still 10 feet. So when we're looking here at this particular graph, what it states is that the height of the basketball hoop is at a certain height, and as time progresses, the height has remained constant. It is the same throughout time. So this is what it's talking about. However, the height of a basketball has not changed. Which graph best shows this? So this graph here shows how the height of the basketball hoop has not changed. So it would be A. But I want to talk about B. B, what this states is the basketball hoop was pretty much at 0, and then over time, people kept saying, hey, okay, the basketball hoop's going to be this, and then it's going to be this, and then it's going to be this, and then it finally arrived at 10 feet. And so it started, the basketball hoop was at 1 feet, and then 2, and then 3, and then so the height of the basketball hoop gradually changed as time increased. And that's not the case, so that doesn't represent. Also here, you know, the basketball hoop started about, I don't know, whatever this is, whatever this represents. And then over time, the basketball hoop kept increasing. So that is not representative of the situation either. So our answer is clearly A. Okay, so let's go on to example 2. Okay, example 2, this is a problem-solving application. It says Jared parked his car in the supermarket parking lot and walked 40 feet into the store and to the customer service counter, where he waited in line to pay his electric bill. Jared then walked 60 feet to the back of the store to get 2 gallons of milk and walked 50 feet to the checkout near the front of the store to pay for them. After waiting his turn and paying for the milk, he walked back 50 feet to his car. Sketch a graph to show Jared's distance from his car over time. Use your graph to find the total distance traveled. Okay, perfect. So I'm going to go ahead and zoom. First I'm going to figure out the important information step by step, referring to his distance from his car. So it said Jared parked his car in the supermarket parking lot and walked 40 feet into the store and to the customer service counter. So the first distance he went was 40 feet, and he ended up at the customer service counter. Okay, then it states the next thing. It says where he waited in line to pay his electric bill. Okay, so that's important because he didn't move. However, time still went on while he is waiting, so we need to go ahead and account for that in our graph. The next thing states that Jared then walked 60 feet to the back of the store to get 2 gallons of milk. So 60 feet to get 2 gallons of milk. And then he walked 50 feet to the checkout near the front of the store to pay for them. Okay, so then he walked 50 feet to the checkout. And then after waiting for his turn and paying for the milk, so that's another thing, he waited. He's waiting his turn to pay for the milk. He walked back 50 feet to his car. Okay, so we're just going to start with the first thing and move from there. So we have a graph here. And the graph, the x-axis is referring to the time, and here on the y-axis is the distance that he traveled from the car. So we're talking about the distance from the car. So let's go ahead and get started with this one. So the first thing that Jared did, so time began, he's in his car, time hasn't started, but when Jared gets out of his car, and he goes into the supermarket, he walked 40 feet. So as time begins, I don't know how much time passed by. It doesn't tell us that, but we do know that time advanced. So we started here at 0, 0. Time was at 0. Distance from his car was at 0 because he was inside his car. Now, once he opened the door of his car and started walking out, that's when time begins. So I'm going to say that he walked, time went on, and he went 40 feet into the customer service counter. Now, while he was at, so that's this yellow part right here, 40 feet to the customer service counter. Now, while he was at, the next thing is where he waited in line to pay his electric bill. So at that point, he did not go any further away than 40 feet from his car. Time just passed. So we're going to stay at 40 feet, but time is going to pass for as he waited in line. Okay, so that kind of corresponds with this. This is the waiting in line to pay his electric bill. Now, after that was finished and that time period is done, then what Jared did is he walked 60 feet to the back of the store to get 2 gallons of milk. So he is continuing to go further away from his car, and it's 60 feet from this point. So if you look, each of these lines are in 20 increments. So time is going, he went 20 feet, 40 feet, and then 60 feet here, okay? So 60 feet to the back of the store, which means he's going away from his car, so that would be the distance there, okay? Now, after he got the milk, I would say maybe it took him, he goes, he gets the milk, and then he walked 50 feet to the checkout. So right after he gets his milk, he's turning and he's going 50 feet. So that would be to the checkout. That would be, this is 20, 40, 50 would be halfway of that. So it would be 20, 40, 50 would be right there. So that would represent 50 feet to the checkout towards the front of the store. So after he got his milk, he's going back towards the front of the store, which would be back towards the distance. I mean, he would be going in the direction back to his car. So that means the distance away from the car would be getting smaller. So now he is only, if this was 50 right there halfway, now he's 50 feet away from his car. So then it says, after waiting his turn to pay for the milk, so he's waiting, he's still the same distance, but time is progressing. Okay, so he's waiting to pay for his things, so that's the orange here. Okay, after he does that, then he walked 50 feet back to his car. So let's see here, 50 feet. This would be, from here to here is 10 feet, and then that's another 20 would be 30, and then another 20 would be 40. And there we have for the last bit right there. He walked back to his car. So this is an example of a graph that could represent this situation. So now what I want you to do is I want you to check it out. I want you to try to do this same thing on your own. Oh, wait, we're not done. I'm sorry. I forgot what it said at the end of this is it says, use your graph to find the total distance traveled. And so that's what we need to do to find the total distance traveled. So let's go ahead and look at this. Okay. First, we're at the car. And then he went 40 feet to the customer service. So this represented 40 feet. Here, he did not move any distance. Okay, he was in line, the customer service line, so no distance was traveled. Then here I'll make it bigger so we can see everything. Okay, yeah. So this was the initial 40 feet to the customer service. This is where he waited in line, so the distance. He did not move. Then he went 60 feet to get a gallon of milk in the back of the store. So this represents 60 feet. Then after he got his gallon of milk, he went to the checkout near the front of the store. So we went back in the direction towards his car, 50 feet. He waited in line to buy his things, and after he bought them, then he traveled back to his car, which was a total of 50 feet there. So if we want to find the total distance, which is asking the total distance traveled, we're just going to add up all of these numbers. So we're going to add up on the side 40 plus 60 plus 50 plus 50. Okay, that's all 0. And then 4 plus 6 is 10, and 5 plus 5 is 10, and 10 plus 10 is 20. So the total distance traveled was 200 feet. The total distance Jared traveled was 200 feet. All right. So that would be our answer using the graph.